here are the answers to the quiz that we had today on chapter 29. And the first question talks about a circular loop of radius 0.10 meter rotating in a uniform magnetic field of 0.20 Tesla. Find the magnetic flux through the loop when the plane of the loop and the magnetic field are perpendicular. So if this is the magnetic field, the plane of the loop is perpendicular to the magnetic field. But remember that we always take the angle with the perpendicular drawn to the loop, which means the magnetic field and the perpendicular drawn to the plane of the loop are now parallel. Okay, and if they are parallel, the angle is 0 degrees, and the flux is given by B dot A, which is BA cos theta. Cos 0 is 1, and therefore it's 6.3 times 10 to the negative 3 Tesla meter squared. And this one, 5 ampere at 110 volt flows in the primary of a transformer. Assuming 100% efficiency, how many amps at 24 volt can flow in the secondary? So you give an IP, 5 ampere, VP, VS, and you got to find IS. The relation is VP by VS is equal to IS by IP. And when you plug in the numbers, you get the secondary current is 22.91 ampere. In the third question, this transformer has 80% efficiency. It steps the line voltage. Okay, you got to take the line voltage as 120 volts here. Although it's not given, you know that's the line voltage, 120 volts. So 120 volts is on the primary. I'm going to change that to 120. And the secondary voltage is 2.9. The secondary current is 240 milliampere. You got to find the secondary current. Now power is given by the product of current and voltage. So since the secondary power is only 80%, which is 0.8, right? 80 by 100 of the primary power. That's why we get this equation. Secondary power is 0.8 times the primary power. Rearrange that and change the VP to 120 to get the answer as 7.25 milliampere. In the fourth question, 2 amperes in the 100 turn primary of a transformer causes 14 amperes to flow in the secondary. How many turns are in the secondary? Okay, NP 100, you got to find the secondary number of turns. IP is 2 ampere, IS is 14 ampere, straightforward. Remember that it's, NP by NS is IS by IP. Okay, so just notice that and substitute, calculate, you get 700 for the turns in the secondary. And in number 5, there are 2 transformers. A has 300 turns on its primary, 500 on its secondary. Transformer B has 250 on its primary and 1000 on its secondary. Same voltage is applied at the primary of both transformers. The secondary voltage in transformer A, that should be A, has an amplitude 50 volt. What is the amplitude of secondary voltage on transformer B? So transformer 1, remember that that's the equation between voltage and turns. And from there we can find the primary voltage, it's 30 volts. And since the same voltage is applied, now you can use the same equation, find Vs. And remember that VP is 30 volts and get the answer 120 volt. A generator produces 60 amperes of current at 120 volt. The voltage is stepped up to 4500 by a transformer and transmitted through a power line. Find the number of turns in the secondary if the primary has 200 turns. So secondary voltage is 4500. The primary voltage is 120. Primary current is 60 ampere. Primary number of turns is 200. You got to find the number of turns in the secondary. Rearrange this equation. $7,500. So you really do not need the current in the primary. We did not use it. Here a coil of 160 turns and the area 0.20 meter squared is placed with its axis parallel to a magnetic field of 0.4 Tesla, and the magnetic field changes from 0.4 Tesla in the x direction to 0.4 Tesla in the negative x. Now that means the change in B, not 5B actually, that's B, change is 0.8 Tesla because it goes from positive 0.4 to negative 0.4. So it's 0.8 Tesla. From that you can find the change in flux because it's just multiply the area with that. You get 0.16 Weber. And then because there are 160 turns, the total flux is N5B, which is 25.6. Now use Faraday's law, is dN5B by dt. And you get 12.8 volt as the EMF. But the power is the product of voltage and current. And current here is just EMF divided by resistance. Okay, so that's I, EMF by resistance. And then you get 10.24 watts. This question, 50 turns, and you're asked to find the peak. I know you've asked to find what? So that's the eighth one. You're asked to find the resistance of the coil. It says the average power produced is 50 watts. Now, the peak EMF is given by this quantity, NBA omega, that's the maximum. And remember that omega is 2 pi f. And once you get that, you can find the RMS because RMS is E naught by root 2. And then the IRMS is ERMS by the resistance, that's just Ohm's law. And then power, average power is just the product of ERMS and IRMS. Okay, that's average power. So that will be 50, which is given as 50. So 50 is equal to that. Solve that equation to find the resistance. 225 ohms. And then that brings us to the ninth question. In this question, the AC generator 40 turns, area is given, and it rotates in a uniform magnetic field, constant frequency of 55 hertz. What's the maximum induced EMF? Okay, so that's E naught. And what's E naught? E naught is just NBA omega. All quantities given. Again, omega is 2 pi f. So 332 volt. A square coil of wire with 15 turns, area given, placed parallel to a magnetic field of 0.75 Tesla. The coil is flipped, so its plane is perpendicular to the magnetic field. in 0.05 seconds. What's the magnitude of the average induced EMF? So the coil goes from being parallel to perpendicular. So that is the coil initially, and if that's the magnetic field, the plane of the coil is now parallel to the field, but you take the angle always with the perpendicular drawn to the coil. So the angle now between the magnetic field and the perpendicular to the coil is 90. Okay, theta is 90, theta I, but theta F is 0, and flux is BA cos theta. Now initial flux is 0 because cos 90 is 0. Okay, final is 15 times, put all those numbers, and you have cos 0 here, so that'll be 1. So you get the final, and EMF is the change in flux, which is 4.5 minus 0 divided by the time. That gives you 90 volt. So EMF, induced EMF, is the change in flux which went from 0 to 4.5 in that many seconds, right? So 90 volt. In this question, a conducting loop in the form of a circle is placed perpendicular to a magnetic field of 0.5 Tesla. Here the area of the loop decreases. Okay. So again, induced EMF is d phi b by dt, but phi is b times a. B is constant, area changes. That's why I've written it as b dA. So it's b dA by dt. The change in area is given. Actually, that's change in area per second. So time is 1 second. And therefore it's 1.5 millivolt. This question, actually the word here step up should have been step down. Because as given in the problem, the number of turns is 3:1 between its primary and secondary. So that means the primary has 3 turns and secondary has 1, which would make it a step down transformer. Because if you take it as step up, you're never going to get the answers given. So that's a typo, and therefore you have to take it that way to get the answer. And then if you look at the question carefully, you see that the ratio went from 3:1 to 24:1. So since the number of turns in the primary has gone up 8 times, that's from 3 to 24, therefore the voltage in the primary will drop 8 times, or in other words, the current in the secondary will increase 8 times. Now when the current increases 8 times, the power increases 64 times, because power is I squared times the resistance, and the square root of 8, if you take the square root of 8, you get 64. Voltage is 8 times less in the secondary, current is 8 times more, and therefore the power, which depends on the square of the current, is 64 times more than what it was before. It was 100 before, so it's 64, 100 watts finally. Here the cross-sectional area is given. It's perpendicular to a field that changes or increases from 0.2 to 2.8. Once again, Faraday's law. This time the area is constant, it's the field that's changing. So A is kept constant, it's dB by dt. You see that difference? And dB, so that's the area in meter squared. And the change in magnetic field strength is 2.8 minus 0.2. So you get that voltage, and then to find the current divided by the resistance. So that's 2.95 milliampere. This is a conceptual question. A circular loop of area 25 centimeter square lies in the plane of the paper. An increasing magnetic field B is coming out of the paper. What's the direction of the induced current? Okay, so induced current has to be clockwise because the induced current has to set up a magnetic field that opposes the change in field that produces it. And what's happening to the field here? The field is increasing, right? Because the question says an increasing magnetic field. So the induced current will produce a magnetic field that goes against it. So it opposes the original magnetic field, and since it's increasing, this magnetic field has to be downwards. Because the other one is increasing, this will try to be in the opposite direction. And by the right hand rule, if the magnetic field is going to be down, then the current has to be clockwise. Just hold your right hand and check it out. So that's why the current is clockwise. The next one is again a conceptual question. And if you look at this diagram, you know the positive charges are up here, the negative are up here. That means the negative charges moved down, the positive charges moved up, which means the current is upwards. Because current is always in the direction of motion of the positive charges. So current is up. Now if the current is up, then again by the right hand rule, the magnetic field has to be along this axis, which is the negative x-axis. It's quite difficult to explain this without some kind of a simulation, but hopefully you understood. The next one is again a conceptual question. Now in this case the bar magnet is moving up along the vertical axis, and as the magnet approaches the coil, it induces an electric current in the direction indicated. Okay, so if it's a clockwise, no, that's a counterclockwise current. Look at that. If it's a counterclockwise current, that is like the North Pole. See how I've written N? Isn't that looking like counterclockwise? So this counterclockwise induced current behaves like a North Pole, and induced current always opposes whatever is producing it. Since this is coming up and it has to be opposed, this must be the North Pole. Because if this is North Pole and this is North Pole, that's a force of repulsion trying to oppose it. That's why X is there. X is, when I take a second look at this, this is a little confusing, this question, because if you look at it from below, now it appears to be clockwise. So if it is a clockwise current, then it's a south pole. Oh. If it is a clockwise current, then it's a south pole, and if it's a south pole, then it has to oppose it, so this must be a south. Yeah, really, this circle, you can, if you look at it from below, it's not very clear, but if you look at it from below, you have to make it out that it is a clockwise current. Okay. And in this question, the magnetic field is coming out of the paper, and as this frame just enters, the force is going to be towards this side by the right hand rule. But when it comes to the center, you have a current that goes up through this part and then here down through this part. So the forces acting on both will be equal and opposite, cancelling out. That's why the force is zero. But as it leaves, now this part is out of the magnetic field, so there's only a force on this part. So same thing here, there's only a force on this part because this part is still outside the magnetic field, right? But here there are equal and opposite forces acting on both sides, cancelling out. Okay, that's why the answer is C. And this is an easier one because it says if the number of turns in the secondary is less than that in the primary, then surely it is a step-down transformer. If it's step up, then it's going to be greater number of turns in the secondary than in the primary. And number 19, the coil is lying flat on a level tabletop. Let me get that question first. Okay. In a region where the magnetic field vector points straight up, as shown in this diagram, the magnetic field vector is straight up. The magnetic field suddenly grows stronger. Okay, so the field which is straight up is increasing. And if it's increasing, the induced current, when it's set up, should produce a magnetic field that's opposite to this. And therefore, it has to be in the clockwise direction, because only a clockwise direction by the right-hand rule will produce a magnetic field which is down. Okay, so the magnetic field has to be opposite to this. Why? Because it's increasing. If it was decreasing, then the magnetic field would have been in the same direction. Okay, so that is the concept that you have to get from there. And the last one talks about a constant magnetic field applied to a rectangular loop of area given, and the area changes. Oh, this is like we had done before. So B dA by dt. So B times the change in area divided by the time, 4.375 times 10 to the minus 4 volt is the answer. I try to make it as clear as possible, but you got to get those distances clearly. Thank you and good luck for the exam.